Hi everyone, my name is Jordan Hu, and I'll be presenting pattern-aware data augmentation for LiDAR 3D object detection. This work was developed in collaboration with Stephen Waslander at the Trail Lab at the University of Toronto. One of the most important sensors in the autonomous vehicle stack is the LiDAR. In fact, many state-of-the-art methods use LiDAR as the primary sensor for 3D object detection, because it obtains highly accurate depth information of the surrounding environment. This, of course, is extremely useful for localizing objects. However, because of the sole reliance on the LiDAR, the performance of LiDAR 3D object detectors tend to degrade at farther distances. The performance degradation stems from two underlying issues: the density variation when increasing distance from the ego vehicle, and the lack of training examples at farther distances in current autonomous driving datasets. The density variation across distance is inherent to the way the LiDAR captures data of the surrounding environment. Since the beams are sent at slightly different angles, the scan lines and points will naturally diverge away from each other as they move farther away. This results in lower point densities on detected objects at farther distances. We can see an example of this in the Kitty dataset. Here we have cars detected at 15, 30, 45, and 60 meters. As we increase the distance from the sensor, the number of points on the detected objects tend to decrease. The second issue is the imbalance of training examples across distance. Here, we see equal element histograms of objects across distance in Kitty. Most of the examples are concentrated within the 15 to 25 meter range, and a general skew towards objects closer than 20 meters. This issue is exacerbated by the fact that Kitty only has 8,000 LiDAR point clouds for training. The small dataset size is slightly alleviated with data augmentations, but this still results in an imbalance of training examples across distance. So, not only do we have less points to perform object detection, there are only a few training examples at far range. What this results in is performance degradation at farther distances. We can see that this trend extends to many, if not all, LiDAR object detectors such as second, point pillars, and PVRCNN. We tackle the second issue of data imbalance across distance by introducing pattern-aware ground truth sampling, a data augmentation method that increases the number of objects at farther distances to train on. By utilizing the natural divergence of the LiDAR point pattern, we can simulate realistic objects detected at long range for LiDAR 3D object detectors to train on, and therefore increase the performance at farther distances. In particular, we increase the performance of PVRCNN by more than 0.7% at distances greater than 25 meters. To get a better understanding of performance across distance, we also use equal element AP bins rather than fixed distance intervals to evaluate our method. This gives a fairer comparison by equalizing the number of elements in each distance bin, and is also more flexible to different dataset distributions across distance. Of course, data augmentations have already been used in training 3D object detectors. Some include affine transformations on the point cloud, as is the case in translations, rotations, or scalings, as well as point removal or addition methods such as ground truth sampling or frustum dropout. These methods can be applied globally, where the augmentation is performed on the entire point cloud, or locally, where the augmentation is only performed on the points within a ground truth box. The table here shows some common LiDAR 3D object detectors and the data augmentations that they use. Most object detectors use global affine transformations along with ground truth sampling, while some also use local augmentations for additional perturbations to the original dataset. Pattern-aware ground truth sampling builds upon ground truth sampling from second. Ground truth sampling works by first creating a database that contains ground truth bounding boxes along with their overlapping point clouds. Then, during training, the database is sampled for each class and added to the scene to increase the number of positive examples to train on. Pattern-aware ground truth sampling takes this a step further by downsampling some of the ground truth samples using LiDAR characteristics in order to simulate more objects at farther distances. Here, we have an example of the effectiveness of the downsampling. On the left is a car detected at 15 meters, and on the top right, we have another car at 30 meters. Both of these are real point clouds from the Kitty dataset. Using pattern-aware ground truth sampling, we can realistically simulate objects at far range. In this case, we can downsample the car at 15 meters to obtain a realistic point cloud of the same car, but as if it was detected at 30 meters instead. There are a few steps needed to perform pattern-aware ground truth sampling. First, the point cloud is represented in spherical coordinates and partitioned into evenly spaced angular divisions. This is dependent on the LiDAR specifications. For example, the Velodyne HTL64E has 64 channels with 0.4 degrees polar angular resolution. Using this information, we can split the point cloud into 64 angular bins with 0.4 degree spacing along the polar angle direction, and likewise for the azimuth. The angular divisions can then be sampled to simulate farther objects, such as sampling every other division to simulate an object twice as far as the original object. Finally, the downsampled object can be moved farther into the point cloud. Let's take a look at a bird's eye view projection as an example. Since it's a top-down view, only the azimuthal angular divisions are shown, but the same process occurs along the polar angle. Suppose we have two ground truth boxes shown in blue inserted into the point cloud. We divide the point cloud into equally spaced angular divisions. Then, we sample every other division indicated by the slices highlighted in green. Next, non-sampled points, or the points not in the green slices, are removed from each ground truth box. Finally, we can move the downsampled objects further into the scene to simulate objects detected at far range. Here we show the resulting point clouds used for training with different augmentation methods. On the left, we have regular ground truth sampling, while on the right, we have pattern-aware ground truth sampling. As you can see, there's a clustering of objects closer to the LiDAR with vanilla ground truth sampling. By using pattern-aware ground truth sampling, we increase the variety distance-wise of samples, effectively reducing the data imbalance across distance during training. Our primary experiments are done on PVR-CNN and KITTI. As a baseline, PVR-CNN is trained with its standard data augmentations, which include global affine transformations and ground truth sampling. We then compare this to PVR-CNN, but with pattern-aware ground truth sampling included. Through our experiments, we found that downsampling ground truth objects 40% of the time with minimum thresholds of 5, 200, and 200 points for cars, pedestrians, and cyclists respectively produce the best overall results. As an additional baseline, pattern-aware ground truth sampling was compared to some similar point removal or noise methods in PPVA, specifically frustum dropout, frustum noise, and random drop. Overall, pattern-aware ground truth sampling provides a slight performance increase over all classes compared to the baseline on the KITTI validation set. Unlike the augmentations used in PPVA, where there is mixed performance on different classes, pattern-aware ground truth sampling improves all classes. The benefit of ground truth sampling can be seen through equal element AV bins across distance for the car class. We see increased performance at distances past 25 meters, with the largest increase at the 30 to 35 meter range. Surprisingly, pattern-aware ground truth sampling also increases performance at extremely close distances, which may be the result of better performance on truncated objects from the camera viewing frustum. We can also see the effect of pattern-aware ground truth sampling on the data imbalance across distance. For this experiment, 5,000 samples are drawn from the KITTI ground truth database. As expected, the vanilla ground truth sampling results in a similar skewed distribution as the original KITTI dataset. In contrast, the resulting distribution across distance when using pattern-aware ground truth sampling is more normal, indicating more far-range examples to train on. Ideally, the distribution would be uniform across distance, but pattern-aware ground truth sampling still results in a less skewed dataset to train from. Pattern-aware ground truth sampling is also tested on other models, second, point pillars, and point RCNN. In general, the performance of second and point pillars increases while point RCNN's performance decreases. We suspect that grid-based methods which use a structured RPN for bounding box proposals provide a more consistent approach to encoding the downsampled bounding boxes, whereas point RCNN is dependent on a PointNet++ backbone with farthest point sampling, and may not capture the downsampled ground truth objects well. In conclusion, Pattern-aware ground truth sampling uses the natural diverging point pattern of a LiDAR to simulate objects at further distances. By doing so, the performance of the object detector is improved, especially at far range where the amount of examples in current autonomous driving datasets is low. Equal element AP bins also gives us a systematic way to understand the performance of object detectors across distance by equalizing the number of samples in each AP bin. However, pattern-aware ground truth sampling does not consider reprojecting the points when downsampling objects. Realistically, if a car was detected at farther distances, the laser points would not be removed, but hit other objects in the scene. Additionally, the added ground truth points are not entirely consistent with the LiDAR scan, as there is no consideration for occlusions within the scene. A future extension would be to ensure pattern-aware ground truth sampling adds augmented objects while ensuring an entirely realistic LiDAR scan.